So, hello everyone. My name is Samuel. We're here at the R&D team of CloudWalk, and today I'm presenting the paper Large Concept Models, Language Modeling in a Sentence Representation Space. This is a paper from Meta that was released at the end of 2024, so almost two months ago. And so let's start here. So as an introduction, we all know that current LLMs operate at a token level. So they are trained to receive a sequence of tokens and predict the next token. And they are optimized at this token level. But what they argue in the paper is that humans process information at multiple levels beyond single words. So when we are like making a thought or trying to arrange some thinking, we don't think like at every word that we are going, don't plan every word that we are going to say. Usually our planning goes by follows more of a hierarchical structure. So we think first on big topics, and then as we go down, we get more specific, getting into the words. But we can also, and we can also like present the same idea in different words or in different modalities, in different languages. We can represent concepts in different ways. So that's the goal that they are trying to aim. Like they're trying to build a model that can reason at a more semantic levels, not just being attached to words. And they mentioned in the paper also that you can argue that using tokens, the large language models can end up understanding this hierarchical structure of thinking, but they are not directly designed for this. So it's kind of like an undirected achievement of, if this is the case, then undirected achievement of the design of the LLM. So their goal, as they stated, is to create a model operated on language agnostic concepts. So regardless of the language, regardless of the modality, they want to model these concepts. And this comes for a vision that they have in Meta of more human-like AI. They have other products that try to attach this more human-like AI, and this is one of them. So this is a quote that we get from the paper, that they aim to model the underlying reason process at a pure semantic level, not its instantiation on a specific language. And so putting more concrete, they define this concept that we are talking here as an abstract atomic idea, and they model concepts as synthesis. So, because they assume that sentences are usually the way that we express a coherent idea. And maybe that's not the best like premise, maybe not the best way to model a concept, but at least it's like a point to start so they can develop their model. This here is a very long paper, more than 40 pages. So I try to like cherry pick the most interesting topics, the general idea, but they develop like many approaches and they go deeper in their explanation. So I'll not be able to like talk about all the mentioned in the paper, just like the main topics. So here's having said that, here's an example of a summarization test that they present in the paper about how summarizations would work in this embedding space of concept. So you have this short history here about Tim that wasn't very athletic. He thought that would change if he joined a sport. He tried several teams. He didn't make cut for any of them, so he decided to train on his own. And then this summarization task in this embedding space, they just like summarize all of these 4 points in just this same idea, and then get to the same conclusion that he decided to train on his own. So this is a kind of example that they give on the paper about how reason in this space of concepts, how that be done. And so going to the actual architecture of the model they propose, they're composed of three main parts. You have an encoder into the concept space, so we have here the words of the sentence. They are encoded in this concept embedding. They use this encoder and decoder called SONAR, which I will talk a little bit more later, which was designed by Meta as well. And then they encode the concepts, and then these concepts goes through the large concept model itself. One thing that is very important here, and they highlight a lot on the paper, is that one of the main goals that they have was to decouple the large concept model from the embeddings, the encoding, this encoding part. The idea was that the large concept models will be like freely to operate just on these embeddings, and regardless of the source of the embedding, if it was image, text, what language it was, regardless of it, the concept model will just operate on this concept embedding. So all this, the encoder is fixed and the decoder is also fixed. This is not learned with the concept embedding, because they try to decouple it so they can be freely as possible and the input can be as varied as possible. So these are the three components. Have the encoder of the sentence, and then go to the large concept model, which predicts the next concept, and then we have the decoder again, using SONAR, and then to convert it back to words. And so, like before going deeper into the architecture, I think it's worth mentioning like some data pre-processing that they did. So just at first in the segmentation step, they use segmented in text or in spacing as segmenters, and they cap the sentence at 200 characters at max, so the sentences don't have very different sizes. And this can be an issue because depending on the kind of text that you have, you can have longer sentences representing an idea or smaller sentences. So, but they choose like to cap at maximum of 200 characters because just to standardize. And they use SAT as shows better performance, and they merge consecutive paragraphs to the training. If the paragraphs is too small, they merge of them. And the SONAR embeddings, just like I mentioned here, they pre-computed them before for efficiency. They stored in floating point 16 precision, and it was processed 4 billion documents, 300 billion sentences, and it was an average of 27 tokens per sentences and 88 characters per sentence. And so now talking a little bit more about the encoder-decoder, about SONAR. It was also developed by Meta. It's an embedding space, highly semantic. It has great scores on semantic tasks. It was trained as an encoder and decoder architecture, so you operate both in the beginning and in the end of the model. As I said earlier, the large concept model operates directly on SONAR concept embeddings, and hence it can perform reasoning on all supported languages and modalities. So all this input part and output is handled by SONAR. It supports 200 languages as text input and 76 languages as speech input. So a lot more flexible than they have on many LLMs today. Now, going to the actual large concept model, they propose 3 different architectures for the three different implementations for the concept model. One they call it base LSM, the other diffusion based LSM, and the third one a quantized LSM. The base LCM is very similar to an LLM to predict next token, but instead of tokens, they use the concept embeddings. So the prediction is done in the concepts embedding space. The main component is this transformer decoder here, you have at the beginning, at the output of the transform, you have this pre-net, which is basically normalizing the embeddings and mapping to the transformer space. And then the post-net does the opposite operation. It's mapping the SONAR embedding dimensions again and denormalizing the values. And they use MSE to train as a metric to train the model. So that's it. It's very similar to an LLM, but using these concepts embeddings instead of tokens. And one thing they mention, that can be an issue here, is that the model is trying to output a very specific concept. So they try to output a very specific sentence, but there are many possible sentences that could make sense, as you can tell the same thing with very different words, very different sentences, and so a lot of different outputs may be still valid considering the same input. So because of this problem, they were inspired to create the second architecture, which is the diffusion-based LCM, which is inspired by the challenge of having minimal plausible outputs for a given input. And this challenge is being very explored in the image domain. So if you ask, for example, an image generator to create an image of a cat, there's a lot of possible, still valid answers for this cat. I want a black cat going down the hall. There's a range of almost infinite possible good answers to this prompt. So they're inspired by this and creating a diffusion-based LCM. And just a recap about diffusion models, the mathematics behind diffusion models are kind of complex, but the general idea of diffusion models is trying to learn the path between a noisy representation to a clear representation. So during training, you get a clear image, and then you iteratively add noise to this image, and then the model will try to learn the path. And you add noise until you have a complete noise image, and then your model will learn the path between this clear image until the noisy representation. And so during inference, you start with a noise image, and then you iteratively remove the noise, add and get to a clear image. And you can condition the noise removal to a prompt. So your model will know, for example, in this example here, your model will know the path between a noise image to a clear image of a cat, of a laptop, of something sitting on the top of other. So they use this prompt here to construct the image of a cat sitting on a laptop. So that's the basic idea of a diffusion model. It's basically learning paths between noisy representations to clear ones. And what this, I'm not talking about the actual diffusion model that they use here. The idea basically is iteratively add noise to a concept embedding. No, just one step back. You have a sequence of concepts in your input, and then you get the last concept, and then you add noise to this concept. So during training, and during inference, you had the previous clear concepts as context, and then you iteratively removes the noise from the noise concept to get the next one, the prediction for the next one. So yes, that was saying here. You iteratively remove this noise to get to the clear concept, and they implement this architecture in two different ways. The first one is called one-tower LCM, which you have here. The zero here indicates that these concepts are clean, there's no noise. And then you have this noise concept here at T. So you pass this to a transformer decoder, and then you denoise this as steps, giving this previous concept here. And then you get your denoiser output here. So that's the basic idea of the diffusion-based implementation. And then they make another variation of this, which is called the two-tower LCM. The main difference here is that they basically separate the encoding part of the context from the denoiser step itself. So we have the transformer decoder here encoding first the context embeddings, and then they pass to the second block here, which is the denoiser, and then the cross-attention mechanism here pays attention to the denoiser concept that you are trying to denoise, and to the context embedding to produce the denoised concept at the end. And as I will show later, these both implementations show like almost the same results. So, but they tried this different approach here. And the last implementation is the quantized LCM. Why they do this? They try this implementation. Diffusion models usually are used in a context of continuous spaces. So images, audios, and this was an attempt to create a method that accounts for the discrete nature of text data. So the SONAR embedding spaces are discrete space, and they are using a method that works really well for continuous spaces. So this was an approach to try to account for this. So they first quantize the SONAR representations and then model on these discrete units. And they try to do exactly the same architecture of the diffusion model, but instead they are iterative generation of SONAR embedding based on intermediate quantizer representations. And this approach doesn't work that good, but it's like an attempt to solve this discrete continuous problem. And now here they have a lot of comparison between the models, but I chose this one here to talk about how they perform. These models, they have around 1 billion, almost 2 billion parameters. So they compare with this small llama here that has almost the same parameters. So you can see here that the base LCM was like really below the other two. The best ones was the diffusion based, both 1 tower and 2 tower, and the quant was a little bit worse, but still like much better than the base. And yeah, the base one, like they show a lot of metrics comparing these architectures, and the base one only outperforms the others in the L2 metric because of the training function that were used. It kind of was objective to this metric, so it was the only metric that they outperformed the others. And all of the others, they were like really worst. So the best implementations apparently are the diffusion ones, and both 1 tower and 2 tower with very, very similar results. So one thing that the result that I found most interesting was the comparison with other popular LLMs. So as I said, the model that they trained, the first one, was around 2 billion parameters. So they decided to choose one model, so they choose the 2 tower, and they decided to scale it to 7 billion parameters so it can be compared to other language models. So they compared with Llama, Mistral, all of this for here. And as you can see here, in some tasks, they got very competitive results, in some not that much. But I don't know, it seems like, at least in these data sets and the other one that they showed, it seems like a competitive LLM given the size with a very, very different approach of like handling the problem. So I think that was like really, really interesting. And talking about the limitations that they mentioned, the first one that they mentioned is like the choice of embedding space impacting performance. So even though SONAR was very suitable for the problem that they had, it was not trained on the best data set possible to this test. It was trained on by text machine translation data containing rather short sentences. And these sentences don't contain a lot of things that you have on normal internet data, like links or code or citations. So they notice that the model struggles really hard when dealing with this kind of rather different inputs that we have here. And the sentence, like the translation of this, the meaning of the sentence seems to be like really close. So it was not ideal for, even though it's very suitable, the idea of SONAR, the training data was not that ideal. And they also mentioned the use of frozen encoders. Like if the encoder was trained with the LCM, probably they would achieve great results. But there are like good and bad parts of it. The second limitation is the granularity of the concepts. So, like just the before going into the granularity itself, they mentioned that concept sentences might not be the ideal definition of concepts. Defining a concept as a sentence might not be the best case, because depending on the kind of text that you have, you can develop a concept in a much more longer than a sentence. So this impacts a lot, and the definition, it's easy to implement, but it's maybe not that ideal. And you also have data sparsity. Since there's a little number of repetition of sentences, you have a lot of different possible sentences that you can encode. So this kind of, this ended up being a problem. And they talked about building some concept units, like the idea of stemming lemmatization, where you have variations of the same word depending on the conjugation, depending on the past tense, this kind of stuff, but it's the same thing. They talking about like building those concept units, like this, all this concept means the same thing, so let's map it into this same unit. But it's that challenging to build, but it can be a nice solution for this problem. And the last thing that mentions is the problem of continuous versus discrete representations trade-off. So, as I said earlier, sentence in the SONAR space, despite being represented as continuous vectors, remains a discrete combinatory objects. This makes diffusion models struggle on text modality. And they also mentioned here that the quantized model might be a way to address this, but the limited performance present in this paper may be explained by the fact that SONAR space was not trained to be efficient quantibles, yielding a significant number of codebooks and a large amount of units per codebook. So making it hard to learn meaningful representations. And I found really interesting, like to see the limitations that they present here, because when I first was reading about this paper, the headlines of the articles was like, is Meta killing LLMs? Is tokens bad? So they're like making a huge deal of this concept representation, and the idea seems promising, but when you go to the actual limitations of the problems, you see that there's a lot to explore until get to like state-of-art results. So, but I don't know, I think it's like a very nice attempt, a very nice try from Meta. They said in the paper that this was just a POC that they made, so they probably releasing other versions of this. But I think like it's an interesting way to approach the problem. And that's it. That's it for the presentation.
Thanks a lot, Samuel, for the presentation. Does anyone want to ask anything? Right. Go on, then.
Yeah, very cool paper. You studied from Meta, right? I think I can see a lot of influence from Ian LeCun in there.
Yes.
I remember like a few months ago, he was pushing the idea that we would like to be like iterating and like this process of deliberation that we have inside, where we are manipulating our concepts and recombining, doing that stuff. Currently, it's like LLMs are doing it on the context, right? When they do chain of thought and do that stuff. And he was pushing that idea that it would be very interesting if you could do that on the latent space, right? And it's very, very cool to see that they're actually getting near to have some actual model doing that. It's very cool.
Yeah, it was. It kind of resembles the JEPA model that they were developing. I don't know, I think last year, but it's indeed very like resembles his vision of human-like AI.
Yeah.
Any other questions? Like I have, I was thinking regarding the limitations that were pointed out. Uh, it seems to me that like they mostly are related to the embedding itself, like the how the encoder works and the choice for that. Like I was wondering if there is any way to um, find like uh, an encoder agnostic performance, like for the model. I don't know, because that was my first thought. Like when I checked the paper, uh, the granularity that is lost when you change to concepts or sentences, like the model does, and like it seems to me that the main problems that they face are connected to how information is encoded and decoded, and maybe less of their actual problems are related to the LCM itself. I don't know if you agree, or like if they mention this, like the performance of the model itself, apart from the choice that they made for the encoder.
Yeah, I don't know if it's like it's easier to blame the encoder than the architecture itself, and because it seems to me like very obvious as well that it's very hard to encode concepts in a meaningful way, depending on the training set. So maybe it's kind of easier to blame because you have a lot of good reasons to think of this. But they mentioned like in the limitations in future work, like developing a data set instead of this translation data set that you use for SONAR, creating a data set that is fitted to this problem of concepts and multimodality, and that can handle better this. So maybe this is a future approach that will try to at least try to solve this encoding part.
Yeah, cool. Does anyone have anything else to ask about the paper or to point out?